Hey everyone, welcome back. This is project 2 of the MCP from Zero to Hero series. If you haven't watched project 1 yet, so please check it out first. Project 1 covers the basics of MCP and shows you how to build a simple Confluence MCP server using FastMCP. In project 2, we will take things further and focus on making your MCP server production ready. This project is a comprehensive guide to building an enterprise-grade MCP server with advanced features, including unit testing, multiple transport protocols, authentication mechanisms, and remote server deployment. Project 2 builds on the Confluence MCP server from Project 1, adding features that are essential for real-world production deployments. Here's what you will learn by completing this project. Firstly, how to implement through unit testing for your MCP server using PyTest. How to understand and configure different transport protocols for MCP communication. How to add authentication for secure API access. How to deploy your MCP server to remote environments with proper configuration. Best practices for developing and deploying production-ready MCP servers. Let's talk a bit more about testing. In this project, you will learn how to achieve a complete test coverage for all MCP tools and client operations, properly mock external API calls for isolated testing, use reusable test fixtures for consistent test environments, automate coverage tracking and reporting. And lastly, add a coverage badge to your README file. By the end of the project 2, you will have a robust, secure, and fully tested MCP server that's ready for production use. As you can see in the README, the current test coverage of the repository is only 38%, which is quite low. Let's understand why the coverage is so low and how we can improve it. First, I will run a test suite using uv-run PyTest to see the current state. The output shows that some tests are failing, particularly in the current client tests. Additionally, several files such as config.py, utility functions, and server.py have 0% coverage. We haven't created any test files for server.py, which contributes to the low overall coverage as well. To address this, we will take 2 steps. Firstly, we fix any failed tests to ensure the test suite passes. Secondly, we will increase the test coverage by adding tests for untested files and functions. To understand the failed test cases, let's have our Copilot agent analyze the situation. First, let's get it to run PyTest and review the output to identify which tests are failing and why the coverage is low. The agent will start by running the test suites and collecting the failed test cases along with their error messages. It will also review the relevant test files such as test_client.py, test_tool.py, and config_test.py, which contains the test configurations. Next, it will check the current coverage report. The agent provides an analysis of the main causes for the failed test cases. It contains mocking issues and assertion mismatches, broken fixture setup for FastMCP context, missing test files, specific problems in the client tests such as incorrect module imports. Lastly, issues with the context manager in the app lifespan function. Each of these issues should be addressed separately. It's important to instruct the agent to fix these problems one by one and commit each fix individually. This approach ensures that each change is tracked and reviewed properly. In the past, we've seen that if not instructed, the agent might batch all fixes into a single commit, which is not ideal. For example, the first issue was a module name mismatch in the client test code. Instead of importing from Atlassian.conference, it should import conference.client.conference-client as defining our client.py source code. This was a simple oversight, but the agent was able to identify and correct it itself. Another issue involved using positional arguments instead of keyword arguments in PyTest assertions, such as with the get page and update page functions. This is a convention that was missed during the initial code generation, highlighting the importance of reviewing AI-generated code. While the AI saves a significant amount of time by generating boilerplates and test cases, human review is still essential to catch these subtle mistakes. After making these corrections, the agent was able to generate a comprehensive commit message following the conventional commit standard, as specified in our README file. There was a pre-commit hook failure due to formatting issues. Simply, the agent just ran the rough formatter to resolve them before committing. With these steps, the code for the first set of fix is committed. Now we can proceed to address the next issue. For the second fix, we focus on resolving issues in the test_tools.py file. Here's a summary of the changes made. The first problem was the test expects mock context dot request context dot lifespan context dot conference, but the fixture that got in place in the test file only provided a mock context dot lifespan context dot conference. To address this, we updated the fixture code to create a proper mock context. The test expects the mock context dot request context lifespan context dot conference, but the fixture we got in place only provided mock context lifespan context dot conference. It's missing request context in the middle. We simply just updated the fixture code to incorporate this change. The second problem was a module name mismatch. The test initialization incorrectly referred to Atlassian Conference. It was updated to use conference.client.conference as defined in our client.py source file. The third problem was the async context manager misunderstanding. The agent misunderstood how the async function for the context manager was defined in server.py. Specifically, the app lifespan function was confirmed to be an async iterator of app context. To fix this, we simply just updated the mock context fixture to return a context instance instead of a async generator. We then simplified the static methods inside the tools class to call the updated mock context during the test. This ensured the mock context contains a conference API client, which can be further used by those static tools methods. As a result, the tests in tested_tools.py passed successfully. The changes were committed separately to maintain clear tracking of the fixes. With these fixes, the test coverage increased from 38% to 48%. This is a significant improvement, but there is still more to do. Fix number 3, the config module is relatively straightforward, as it primarily consists of a config class that loads environment variables. To improve the coverage, we make the test simple to implement and result in a full coverage for those config modules. Fix number 4, adding tests for the utility functions. Similar to fix number 3, those utility functions created in project 1 are those basic helper functions, which does the string manipulation, data validation, and API response formatting. Um, for any more detailed implementations, you can always refer to my GitHub repository, which consists of all the source code and test files. Now, I'm not going to show you the full details of the remaining test code generation, as it very much follows the same pattern. It continues with the test_tools.py along with the updates to update_coverage_page.py. What we achieved at the end is 98% test coverage, which is phenomenal and ensures that our MCP server is robust and production ready. If you have any further questions, feel free to leave them in the comments section below, and I will be happy to address them. Now that we've achieved the 98% test coverage, there's one final step to ensure our testing procedure is seamless, integrating PyTest into the pre-commit hook. Previously, PyTest wasn't included in the pre-commit because the coverage was too low and several test cases were failing. Now we've resolved those issues, it's time to update the pre-commit hook. Firstly, we need to add a new entry for the PyTest in the pre-commit configuration file. This ensures that the test suite runs automatically before every commit. We can get a Copilot agent to help us to do this. Just to note that in the final stage, we will need to add a threshold of 90% to the setting. So any test coverage below 90% will fail during the pre-commit stage. After updating the configuration file, we need to reinstall the pre-commit hooks to apply the changes. Just simply run this command pre-commit install that will help us to ensure the updated hooks are active in our local codebase. Lastly, we need to make a small update to pyproject.toml file as well. Make sure it's compatible with the pre-commit hook. With these updates, every commit will automatically run the test suite, ensure that no code is committed without passing tests. This is a crucial step for maintaining the code quality and preventing regressions in a production-ready MCP server. Before we dive into the other sections of the course, I think we should create a quick tutorial on PyTest. If you are already familiar with PyTest and don't feel you need to go through this section, feel free to skip it. For those of you who are new to PyTest and want a refresher on how it works, please bear with me for 5 to 10 minutes as I walk you through the basics of PyTest and explain how it's been used in this project. First of all, what's PyTest? PyTest is Python's most popular testing framework. It makes writing and running tests simple while providing powerful features for complex testing scenarios. It's essentially a testing framework where you can simply run the command run PyTest to generate a test report that shows you whether your test cases pass or fail, as well as the test coverage of your current project. Let me explain a few key concepts. The most fundamental concept is the basic test structure. Tests are functions that start with the prefix test underscore and use a assert statement to check whether values are correct. This is the hello world of basic test examples. For example, we have test underscore basic underscore example function with the test underscore prefix. The result is 2 plus 2, which equals to 4. The assert statement will check the and assess whether the test fails or passes. If the result equals to 4 and it does not equal to 5, then the test passes. The second concept is called a fixture. Think of fixture as reusable components within the PyTest framework. Fixtures provide consistent test data and setup. They are decorated with @pytest.fixture and can be reused across multiple tests as many times as you like. In our real-world example, we have many fixtures under a file called config.test.py. What it does is provide reusable components for certain objects. For example, the mock_config fixture provides a config object that can be used across the whole project. All it contains is a Confluence API config with conference URL, username, and API token. These are all dummy configs used across the test suite, but they need to be called multiple times. You can see the second example with mock_page. This mock page returns a dummy page with page parameters like ID, title, space key, version, and content. This is a dummy page that might get called multiple times, which is why we create a fixture to make our testing more convenient. Here's an example. If we need to test the config values, you can always call mock_config, which returns a config object with all the parameters in it. The third concept is called patching. Patch works like an interceptor when you make an API call or call a certain function. How it works is you put a @patch decorator, and when a conference client is called, it's actually not going to trigger the real conference client. What it triggers is a patched fake conference client that provides dummy data during the test. All it does is to help you verify that your client initialization code can trigger a conference client correctly. We don't actually worry about whether the real API call is made or not. We just need to verify that initialization of the conference client is correct. There's another example where you can mock an environment variable using @patch.dictionary. You can put your conference URL in it, and when we load the config, it will load the fake conference URL during testing. The fourth concept is async testing. If you need to test asynchronous functions, we need to use the decorator @pytest.mark.asyncIO. We use this in test_tools.py when we need to call a function that's asynchronous. Like this get page_tool, we have a page ID and we need to set up a mock response. This is the way we test async functions. The fifth concept is exception testing. Testing that your code properly handles the errors using PyTest @races. You can see we are putting a wrong page ID on purpose. When the exception is raised, we use PyTest @races to check whether the exception is raised properly. The last concept is parameterized testing. This allows you to run the same test with different inputs using @pytest @mark @parameterize. What it does is help you test the same function with 6 different inputs to see if they all can pass the test. So one function with 6 different inputs. That's why it's called a parameterized testing. At a higher level, these are the testing patterns we use in our project. Setup, action, assert pattern. Very easy to understand. We set up mock data, then we take an action, which is normally a function call or API call to check the process. Then we assert the result to check whether it's correct or not. Second is mock configuration pattern. We use the @patch decorator to mock an API response. Then we assert the response is what we expected. The last one is context manager testing. Remember, in this project, as part of the FastMCP server, we use a context manager to manage the conference API client. During testing, we need to mock the context manager so all the conference client initialization can be mocked and handled during testing. These are the test commands you will need for PyTest. Most of them you have already seen in my videos. If you want to generate a coverage report on certain classes or in different report formats, you can always use those extra command parameters and arguments. That's it. Now we have a pretty good understanding of PyTest. If you have any further questions, you can always leave them in the comments section down below, and I will be more than happy to answer them. Let's have a deep dive of the 3 different communication transport protocols. We can start with testing the StdIO protocol. To do this, you can just use the MCP inspector tool without installing it by typing npx at model context protocol /inspector. Once the inspector UI is up and running, it triggers the server.py script, spinning up the server in an isolated environment. For example, if you try the search function, it works as expected and returns the search payload for your PRD document. Next, let's test the Streamable-http protocol. Unlike StdIO, the MCP inspector does not directly trigger the server for this protocol. You will need to spin up the server manually. Running the following command, FastMCP run server.py, and specifying the transport is equal to Streamable-http under the main function. For some reason, this did not work. The inspector will show you an error saying it cannot find this server. Let's have a look at the FastMCP documentation. We learned that the default hosting port are localhost 8000 with the path /MCP. Later, we tried the FastMCP command with the argument being explicitly added. So let's do FastMCP run server.py --transport and -streamable-http. This is working as expected. And if we go to inspector UI, trying the search function, it returns the expected payload. The key takeaway here is that when using the FastMCP command without specifying the transport type, it defaults to the StdIO and skips the transport configuration in the main function. To avoid this, always specify the transport type in the command line arguments for non-StdIO protocols. Alternatively, you can bypass this by running the script directly with UV. You can just hit UV run server.py without specifying the transport type. This triggers the main function where the transport protocol is already defined. Finally, let's test the server send event. According to the FastMCP documentation, the default hosting port are localhost 8000 and the SSE path is /SSE. Although SSE is marked for deprecation in future versions, it still works in the current version. To test SSE, you can either specify the transport type in the main function and run uv run server.py, or use the FastMCP command with the transport argument being set to SSE. When you go to the MCP inspector UI, select SSE from the dropdown and update the URL to localhost 8000 /SSE and reconnect. The search tool worked as expected, returning the payload for the PRD document. Now we've learned about 3 different transport protocols. It's time to look into authentication. Let's go through the FastMCP documentation and see how to set this up. I will come back to the theory after we have something up and running. First of all, we need to check if we have the latest version of the FastMCP. Authentication has just been added into the latest release of 2.6.0. So let's check out our current FastMCP version to see if we need to upgrade it. To do this, we can just simply type in FastMCP space version into the command. As we can see, we only have version 2.3.3, so we actually need to upgrade it. To do this, just type in uv at FastMCP equal 2.6.0. This will upgrade FastMCP from the current version to 2.6.0, then we can start using the latest authentication classes. Let's have a look at how we can set this up. The FastMCP documentation provides a clear guideline on the whole process. First, we need to add the bearer author provider for bearer token authentication. If you are not familiar with bearer token or how the authentication workflow works, don't worry too much about it at this stage. I will come back to the theory once we have something set up. Let's copy the example code into our codebase in server.py. Firstly, import from FastMCP at server at auth, import the bearer author provider. When we start the server instance, we need to add a few more components. Firstly, we need to put this author provider instance before FastMCP server. Now we need to check what we need to include here. To test this in our local environment, we can use a helper utility class called ISA key pair. What this does is generate testing tokens for us in local environment without the need for using an OAuth 2 provider externally. To bring this in, just do another Python import from FastMCP at fastmcp.server.auth.bearer, import ISA key pair. We will generate the key pair before we can use it, so put it before the bearer author provider. And of course, we need to add the auth argument to the FastMCP instance, so the server will have authentication enabled. Unauthenticated users or clients will not be able to make the call to the server anymore. For testing purpose, we can even just print out the token to check and validate whether it's been generated. Let's quickly spin up the server in our local environment to see if it's working. If we run run server.py, you will see it's running and it actually printed out the test token. So how do we validate if the authentication is working end-to-end? One simple way is to validate if we can use a client to make a MCP call to the server. So we can build a simple client using FastMCP. FastMCP can not only be a MCP server, it can also be used to build MCP client. For testing purpose, this client instance we're spinning up is only going to have a very simple MCP call, which is called list tools. And reading through the FastMCP documentation, we just need to pay special attention to the authentication part, see how it's going to be configured. Again, the authentication of the MCP client is based on OAuth specifications. The client will have an authentication header, and in that authentication header, we will put the bearer token. That's normally generated by an OAuth provider, but for testing purpose, that token is generated by the ISA key pair utility class that we used in the server. So we can just create a simple FastMCP client.py file, and it will put the authentication header, authentication token in the header, then make a simple MCP call to the server to list all the tools. If we can establish the connection, it will get a list of all available tools and print them all out. Cool, it's working. So we've got all the tools listed in the response payload now. Now let's prove that authentication is actually working. Let's try to run the client again, but this time without putting the authentication token in the header. As you can see, this time we get an error, 401 unauthorized. This proves that we do need authentication. The bearer token must be added to the header for the client to successfully communicate with the server. Now that we have authentication working, we are approaching the final step of this project, deploying our MCP server to a remote cloud host. Let's compile a server.py that's ready for production use. For production use, we will leverage FastMCP's ASGI server integration capabilities. Let's go to the FastMCP documentation. There's a section that talks about ASGI server integration. We can easily mount this MCP server on a Starlette ASGI server. The good thing about mounting it to a Starlette server is that it becomes a proper backend server, which means you can have multiple routes and different endpoints on the backend API servers. A very typical one is a health endpoint, which becomes very handy when you want to ping this health endpoint to check the status of the server and get a healthy status response. To mount our MCP server, it's very simple. Just mount it inside the route and give it a path /mcp-server. The final path of our MCP server endpoint will be /mcp server/mcp. Apart from that, there's not much to change. We also need to pay special attention to the final main function. It's slightly different from our local server instance. Instead of using mcp.run, we actually need to import uvcon and use uvcon.run. The host URL is no longer localhost. It's 0.0.0.0 for Cloud Run, and the log level should be set to info. That's pretty much it. Those are all the changes we need to make for a production-ready server.py. The next step is containerizing our server and deploying it to Cloud Run. For containerization, we need to create a Dockerfile. Let me quickly go through what's in the Dockerfile that I created for this deployment. Firstly, it will pull the public Python base image 3.11-slim, and it will set up a bunch of environment variables for deployment purpose. For example, it will set up the caching directory for UV, and it will also pull the UV from its public image. Then it create a non-root user to follow the security best practices. It will start copying the dependency files and switch to the non-root user called app and start synchronize and install the dependency packages. In the final step, it will expose port 8000 to work on Cloud Run and run the final command uv run server.py. We also have .docker ignore file to exclude non-production related files. You can see there's a big list of files that won't be copied into Docker container, including the client test files we created for local testing purposes. They don't need to go to the production environment, so we can keep the production environment clean and tidy. Now that we have Docker and Docker ignore set up, the next step is to deploy to Cloud Platform. In this instance, we will use GCP. I will also introduce you to AWS solutions later, but GCP offers the simplest solution for deploying remote servers with authentication at this stage. For deployment, we have a simple shell script. Firstly, it will check for a .env file with environment variables. We need 3 environment variables: conference URL, conference username, and conference personal access token. These get added during the deployment process as environment variables for our Cloud Run instance, so they are not exposed in the codebase. This is also follows the security best practices. We also set up several variables during the deployment in the shell script itself, which includes the project ID, region, repository name, image name, and the version tag. Let me explain the whole process. First, we will have a Dockerfile in our local environment. Then we use the Dockerfile to build a Docker image. Once the Docker image is built, it gets pushed to GCP's artifact registry. Artifact registry is a collection of your private Docker images. If you go to artifact registry, you can see there is already a repository created by me called FastMCP repo. You can create as many repositories as you like, and our Docker images will be saved under one of these repositories. Please pay special attention to the Docker build command. If you are running this on your ARM64 Silicon MacBook, like what I did, we need to add the argument called platform linux/amd64. Otherwise, there will be compatibility issues. That's the instance type that Cloud Run uses, not ARM64 Apple Silicon. Once the image is built and pushed to artifact registry, the final step is deploying a Cloud Run instance based on the uploaded image. That's where you set the environment variables for conference URL, username, and personal access token, along with other parameters. We need to pay attention to this argument. No allow unauthenticated. This means API calls or MCP calls must be authenticated with this Cloud Run job. Now, let's run the deployment script. Before we run it, we need to authenticate with GCP. So just run GCP auth login command, which will ask for access permissions. Once that's successful, we can run deploy.sh to trigger the deployment. It will first start building the Docker image, which will take about a few minutes. Then it pushes the image to artifact registry. As the final step, it will deploy to Cloud Run. The deployment is successful when it says serving 100% of the traffic, and it also provided the service URL. Now we have a server up and running. We need to update our client configuration to connect to the remote server instead of the local one. To establish the connection, we need to firstly understand how authentication with remote server works. Google has documentation on how to deploy an MCP server to Cloud Run with the Streamable-http connection support. For authenticating MCP clients, there are two options. First option is IAM Invoker Permission. It uses a local Cloud Run proxy on your machine to securely expose the remote MCP server using your user credentials. As long as your user credential has rows/run.invoke permission, this solution will work. The second option is to use OIDC ID Token, which uses a Google OAuth library to get OIDC tokens for authentication based on a service account. If this is your first time using GCP, you will need to install the Google Cloud CLI. Just search install Google G Cloud CLI for instructions for macOS and Windows. For option 1, we need to spin up a local Cloud Run proxy using the command from Google's documentation, which is gcloud run services proxy Confluence -FastMCP, and specifying the region to be US-Central 1. Putting port is equal to 3000 if you want to go with the default option, but you can change that to be any port that you want it to be. The local proxy injects your user credentials and uses them to authenticate with the remote MCP server. One important thing to remember, since we are using a Starlette server, it becomes a proper API backend. So the endpoint is no longer /MCP. It's a /MCP-server/MCP. We need to update this in our client script. Once updated, let's run our client again with the local proxy. Boom, it's working. We've successfully proved the first authentication method works. Different from option 1, which uses your user login credentials, option 2 uses an OIDC ID token. We need to use a service account here, so we will be using the service account credentials to retrieve an ID token. OIDC stands for OpenID Connect ID Token. For this approach to work, you will need to provision a service account on GCP. Go to your GCP console and click on Service Accounts, then create a new service account. You can name it Confluence MCP Server and click Create and Continue. Remember to add permissions for invoking Cloud Run Server, which is roles/run.invoker. Once that's ready, just click Continue and you will be able to provision the service account. Once you have the service account ready, click on Manage Keys from Settings, click Create a new key. The new key will automatically start downloading. Once you have the service account key ready in your Downloads folder, grab it and save it in your .config/gcloud directory. Next, go back to your codebase and add an environment variable called Google Application Credentials. This will contain the file path URL of that service account key you just saved. Once that's done, let's look at the script. First, we load the environment variable because we need to know Google Application Credentials location. We also have a token manager created to manage the OIDC ID token. The target audience in this instance is the URL of that Cloud Run instance. The token will initially be set to none and expires at 0 time. The refresh is based on this condition. If we don't have a token equals to none, or it's about to expire in the next 5 minutes, we refresh the token. We need to grab the Google Application Credentials, which is the service account key that's saved in our local folder. We use the ID Token Credentials class to retrieve the ID token using our service account credentials. Once the ID token is retrieved, we refresh it and decode it to check the expiry date. When we get to the main function, firstly, we grab the Cloud Run URL and the token manager. Secondly, we set the transport to Streamable-http with the Cloud Run URL /MCP-server/MCP/. We need to pay special attention to the trailing slash here after MCP. Initially, I didn't add the trailing slash and started getting 307 redirect errors. I'm not 100% sure if this is a Cloud Run thing or just a general requirement, but you do need to add the trailing slash at the end of /MCP to make the whole thing work. The rest of the code is straightforward. We are still just checking and listing the tools. Let's run it and see if it returns a list of tools for us. Excellent. It's working perfectly. We've successfully demonstrated both authentication methods for connecting to our remote MCP server deployed on Cloud Run. Congratulations! We've successfully completed Project 2 of MCP from Zero to Hero series. Let's recap on what we have accomplished. Firstly, we increased our test coverage from 38% to 98% by fixing failed test cases, adding tests for untested modules, implementing proper mocking strategies, and adding PyTest to our pre-commit hooks. Secondly, we look at the transport protocol. We explored and tested all the MCP transport protocols, StdIO, which is used in our local environment, and Streamable-http, production ready, and the deprecated but still functional server sent events. Thirdly, we explore the authentication implementation. We implemented a secure authentication using bearer token authentication with RSA key pair for the local testing purposes. And there are two production authentication methods we did with the Cloud Run on GCP. First one is the IAM Invoker Permission with our user login credentials. You can also use service account credentials with OIDC ID Token. Lastly, we successfully deployed our MCP server to Google Cloud Run. We created a production-ready Dockerfile with the security best practices. We implemented ASGI server integration with the Starlette. And we configured the Cloud Run with authentication requirements. Your MCP server is now robust, secure, and fully tested, and it's ready for production use. This foundation will serve you well as you build more complex MCP integrations and to scale your implementations. In the next video, we will look into some of the more advanced topics and discuss the AWS solution of remote server hosting. Happy coding!